Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself Professor Anjali Pal. We are both from the Department of Civil Engineering of IIT Kharagpur. We have divided this course into two parts. The first part, environmental chemistry, will be covered by me, and the second part, environmental microbiology, will be taught by Professor Sudha Goel. So, this is my module 3 and this is my 13th lecture. In module 3, I am discussing chemical kinetics, and in this lecture, that is the 13th lecture, I will be covering the zero order reaction, first order reaction, second order reaction and integrated rate law. I have already discussed about the rate of a reaction, and I have already discussed about the order and the rate constants and the differential rate laws, how we can apply differential rate laws to find out the order in the previous lectures. Here I will go into details about the integrated rate laws. Say for example, if we consider this reaction, simple reaction where A is the reactant and P is the product. Say for example, this reaction is following zero order kinetics, then from the rate expression we can tell that the rate is nothing but K into C to the power C A, because here it is the reactant is A. So, C A to the power n. This is the rate law or rate expression, and then because it is a zero order reaction. So, we can write the C A to the power 0. So, rate is nothing but minus d C A by d t into K into C A to the power 0, because zero order reaction. So, this is becoming 1. So, it is K. So, from here we can tell that zero order reactions, the rate is independent of the concentration of the reactant, and here K is the rate constant that or specific rate constant that I already discussed in the previous lecture. Okay. Now, in case of zero order reaction, if see, to make it simplified, you know, dCA dt all the time to write dCA dt. So, it is a term if I remove. I have removed the a term to make it little simplified. Okay. So, we have seen from the previous in the previous slide that the rate is minus dCA dt is nothing but K. This is for the zero order reaction. Now, the rate of change of concentration of A with time, as I told already that this is the rate. So, rate always will be expressed in terms of mass per volume per time, that also I told, and it is up to you that how you will, what units you will use for volume, what unit you will use for time and what unit you will use for mass. But the rate constant, you see that in this case the it is the same as the rate. So, for zero order reaction, rate constant is expressed as the same like the same unit as we express for rate. Okay. Now, integrated rate law, it is easier than the differential rate law to visualize and to apply. Okay. Now, if we integrate this, then we will get C is equals to minus k t to change the sign here. So, minus k t plus constant of integration. Now, the constant of integration also we can get by putting t is equals to 0. So, if we think that at t is equals to 0, C is equals to C 0, then we can get the C 0 is the constant of integration. Okay. So, this term is becoming 0, that is why C 0 is nothing but the constant of integration. So, by putting this one we get C minus C 0 is equals to minus k t. Okay. So, if we plot C versus t, okay, then what, how the curve nature will be. So, if we plot C versus t in the x axis and C in the y axis, because it is negative, because it is the reagent concentration. So, it will be with negative slope, okay. It will be negative slope, and the point where it is cutting, it will be C0, that is at time t, it is the concentration, that is we have already told it is C0, okay. So, 0 order curve will be like this if we plot C versus t, okay. So, so what we can do experimentally also, we can do very simple way. We will determine the concentration, we will start the reaction, we will determine the concentration at different times, then we will just plot it. Concentration we will plot versus t, and then we will see whether it is following a linear plot or it is not following a linear plot. This is easy, very easy. Now, in case of first order reaction, in case this is the rate expression, we all know it is, again it is simple, most simple reaction we have considered. So, rate is nothing but k into dCA, Ca to the power n, n is the order. So, when it is a first order reaction, so n is 1. Now, minus dCA dt is equal to k into Ca. So, in this case you have to remember one thing, that what is Ca? Ca is the concentration of A at any time t. So, this thing you have to remember, okay. For any numericals you have to do, or anything you have to kinetic analysis you want to do, you have to remember that Ca is nothing but the concentration of A at any time t, okay. And now, dCA dt is the rate of change of concentration of A with time. So, this is the, I already explained it, that rate has the unit mass per volume per time, K has the unit. You see here K, this Ca term, Ca means a concentration term will go away. So, it will be time inverse, okay. So, K is the reaction rate constant, which is nothing but the time inverse, okay. This is very important to remember for first order reactions, okay, time inverse. Now, for first order reactions, we know the rate expression is like this. So, here you can see that first order reaction proceed at a rate directly proportional to the concentration of the reactant. From the rate expression we get this thing, but this point is very important, since the rate of the reaction depends on the concentration of the reactant, and the concentration of the reactant changes with time, okay. This is understandable. Rate of the reaction depends on the concentration of the reactant, and reactant concentration is changing with time. So, an arithmetic plot of the variation in the concentration of the reactant with time does not give a linear response. So, figure 2. So, if you plot concentration versus time, then you will not get the straight line curve. The curve will be like this, okay, and the slope will give you the, at any point will give you the dCA dt with minus sign, because it is the reagent, okay, reactant. Now, now if we apply the integrated rate law, then on integrating this equation we will get ln C0 by C equals to kT, or you can put it in log term also, log C0 by C is equals to kT by 2.3, or you can do this thing also, log C you can plot versus t. If you plot log C versus t, then you will get a straight line with slope negative, because it is the reactant. So, it will decrease and the cutting point will be nothing but C0. And if you plot ln C0 by C, here it is the log C, okay, or ln C you can plot. So, you will get this type of curve with negative slope, but if you plot ln C0 by C, then you will get a then also you will get a straight line curve. You can see here this is a straight line curve, and it will be with positive slope, okay, it will be a positive slope. So, this is the integrated rate law for first order reaction. Now, previous one we have seen that for the 0 order reaction we have seen that concentration versus time, this will give a straight line, but in case of first order reaction you will see that log or ln you have to plot versus time, then you will get a straight line curve. Okay. This is the difference between the 0 order and first order reactions. These are both are the integrated rate law. Now, one thing is very important, this is another example, it is shown instead of giving A and A is the reactant and P is the product, here one reaction is shown, actual reaction is shown. It is a gas phase reaction, nitrogen N2O5, nitrogen pentoxide. This is in gas phase, it can decompose to nitrogen dioxide and oxygen, and then the rate of this decomposition of N2O5 you can write in this fashion, and then here instead of writing CN2O5, here it is only concentration term it is written. To make it simple, you can write that ln C0 by C is equals to KT, that is already explained in the previous earlier, okay, just previous slide. Okay. Now, ln N2 by N2O5 if you plot against time, then you will get a straight line curve, okay, a straight line curve, because it is a first order reaction. In this case I will explain, let me explain that here you will get first order reaction, actually determined it is a first order reaction. At the same time you can see that the molecularity, if we think about, because I told you that reactions can be thought in two different ways, one is the molecularity, another is the order. So, in this case if you see the, because only one molecule of N2O5 is involved in the reaction, in the balance reaction. So, here molecularity is also 1. But molecularity is 1, here it is matching with the order. Order is also 1, first order reaction, and molecularity is also 1, it is unimolecular reaction. But it may vary also, that is the question. So, means order and molecularity may not be the same. Here it is same, but it may not be the same, that you must remember. Now, one thing is very important for the first order reactions. What is that? This is the half life. Okay. This is also very important for radioactive elements. First, so all the radioactive elements, because they decay by in first order, the reaction is first order, the degradation is first order reaction. That is why in that case the radioactive elements are also characterized in terms of their half life. So, half life is very important for the first order reactions. Now, what is half life? Half life is always expressed in terms of T half, okay, as T half. So, what is half life? Half life is the, say for example, the original concentration is C, okay. Then the time that will be taken for that reactant or for radioactive element, whatever may be. So, to come to its half concentration, means if you start with C, then how much time it will take to come to C by 2, that time period is known as half life. Okay. So, in case of first order reaction, we know that ln C0 by C is equals to KT. So, C0 and then the with that time where it comes to C0 by 2, if we put here C0 by 2, then the corresponding T will be T half. Okay. We can tell that half life as T half. So, here it will come ln2 C0 by 2. So, ln2 and then k into T half. So, the value of ln2 is nothing but 0.693. So, 0.693 by T half is equals to k. Okay. So, k is the specific rate constant which is related to T half, or other way you can tell T half is related to k. Okay. But there is no concentration term here, you can see. That means half life does not depend on the concentration, it is a very characteristic thing. Okay. It does not depend on the concentration. That is why in radioactive elements also you will see, when I will discuss about radioactivity, then you will see that radium, say for example, it has some particular half life, uranium it has some particular half life, it does not depend on the initial concentration. Okay. It is a characteristic thing. Now, if you look into the curve, that is the time in the x axis and the concentration of N2O5, it is giving in the considering this example. Okay. So, you start with 1. If you start with 1, then the half life will be that time that taken to come to 0.5. So, you have started with 1. So, half of 1 is 0.5. So, to come to this concentration 0.15, how much time is taken? That is T half. So, this time is T half. Okay. Now, you start with 0.5. So, 0.5, half of 0.5 is 2.5. So, how much time it will take to come to 2.5? Corresponding to that, this time is T half. So, T half, you have started from here to here, next second one. So, here to here, so this is the T half. So, if you consider from the 0 point, then it is 2 into T half. Similarly, when you start with 0.25, that is here, then half of this is 0.125. So, here. So, here again it is from here to here, the time taken is again T half. So, if you consider from here, it is 3 T half. Okay. So, like this it will continue like this. Okay. And it is first order type, first order curve. Okay. So, you can means you can easily understand that how it goes. Okay. The degradation or decomposition goes with time for half life period, means for first order reaction. Now, second order reaction. Second order reaction is also very common. Many reactions are second order reactions. Okay, here you can see that 2A, the balanced equation is 2A, reactant A is the reactant P. Here second order. So, here molecularity also 2. So, by chance molecularity and order is same here. Okay. So, rate expression is equals to K into Ca to the power 2, because it is a second order reaction. Now, same way integration upon integration, it gives 1 by C minus 1 by C0 is equals to K into T. And here you can see that K the unit reaction rate constant, the unit is this one. You can easily develop from that rate expression, because rate you know, this minus dCA dt or Ca dt. So, concentration term here, here another concentration term to the power 2. So, K will be accordingly, it will have this unit. Okay. Now, for the second order reaction, this is a integrated rate loss. So, second order reaction, if you plot 1 by C here in the y axis and time in the x axis, then you will get a straight line curve with positive slope. The cutting point is 1 by C0. Okay. So, in the first order rate you have seen we have to plot ln C or log C versus time to get a linear curve. In case of 0 order, C versus T to get a linear curve. In case of second order reaction, you have to plot 1 by C versus T and you will get a straight line curve. It is a very simple method actually to know the order of the reaction, because you have the data set. At different time intervals you have collected some samples for a reaction and you have measured the concentration of that particular reactant or product, whatever may be, and then you make a table, and then after making the table you just plot it. You plot it, different plots you have to make, and then you will see which one is following the straight line curve. Accordingly, you can decide which one is the order, what is the order of the reaction. Now, for a reaction, this is an example. Say here in this case, in the previous examples we have shown only one reactant, but here there are two reactants. A is the reactant, the molecularity is here, the stoichiometry 1, another reactant is there, this is the B. So, here the stoichiometry is 1 is to 2 and giving a product. If this is the case, then how will you tell about the rate? I have told you that rate how you can express, but what about the order? How will be the order? What will be the order? Whether you will determine in terms of A or B or both, that is to be determined, because some reactions you may just consider A and you can tell that this reaction is first order with respect to A, this reaction is second order with respect to B, or you can tell that overall order of the reaction is 3. So, how will you tell it? That is very important. Now, the same thing, in many cases the rate of a reaction depends on the concentration of 2 or more different chemical species. The same thing, so in that case that I was explaining in the previous slide. So, in this case you see the rate is K, this is the specific rate constant, Ca to the power m and Cb to the power n. So, you can tell that m and n do not, you have to remember this, that m and n do not come from the coefficients of the balanced equation. It is not like m a plus n b giving product, it is not like that. It may happen like that, but it is not like that. They should be determined experimentally, m and n should be determined experimentally. From the above rate expression we can say that the reaction, if you get this type of expression, then you can tell that this reaction, the considering that reaction is mth order in A and nth order in B, you can tell that, and the overall reaction order is m plus n. A very nice example here, you can see, you can have the idea that it is the reaction of H2PO4 minus and OH minus, it is in aqueous phase reaction to give HPO3 2 minus and hydrogen is a gas. Now, experimentally it has been observed that the rate of the reaction is this one, it is the rate expression H2PO2 minus to the power 1 and OH minus to the power 2. But these two, you see here it is 1. So, you cannot tell from just by seeing the equation, you cannot tell that it will be the, what will be the order. Now, you can say how we can express, we can say from this that this above reaction is first order with respect to H2PO2 minus and second order with respect to OH minus. The overall reaction is 2 plus 1, that is 3. Accordingly, the unit of K you can easily find out. So, I think it is clear from these examples and this how it is explained. You can, now it is your choice whether you will use the differential rate law or you will use the integrated rate law, and to determine the order, and whether you will determine the order with respect to something or you will determine the order with respect to both, that means overall reaction, that is up to you, that is up to you. Then how to know the order of the reaction in a real experiment? Real experiment, how will you do it? I will show in the last lecture actual one experiment I will show how you can determine the order, but these are all theoretically I am explaining to determine how to determine the order. Now, we start before we start what the order of the reaction will be. In a real experimental study we do not know what is the order. Okay. So, how we cannot speculate also. So, how we will determine the order? Okay. In that case we have to take the experimental data, experimental observations, we have to find the data, we have to collect the data. After that we have to try different plots, the 0 order plot, first order plot, second order plot, we have to get. Okay. After that, depending on the which one is the best fit, okay, according to that you can tell, okay, this reaction is having this order. Okay. So, this way we have to determine. Okay. This integrated rate law and differential rate law and how to determine the order, all those things that has been discussed here in this lecture, you can get from the same book that I already have mentioned in previous lectures. Okay. So, you can easily get, and this is very very nice book, both the books are very nice. So, thank you very much.